Hello all, welcome to my channel. In this video, I will explain how to solve a linear programming problem by simplex method, but the question will have lower bound. I have already made a video in which I have explained what is lower bound. I have shared the link in the description. So let's start. The given problem is a maximization type of problem which states maximize z is equal to 10x plus 15y plus 8z as the objective function, and it is subjected to constraints x plus 2y plus 2z is less than or equal to 200, 2x plus 3y plus z is less than or equal to 220, 3x plus y plus 2z is less than or equal to 180. There is nothing new in this LP problem, but the lower bound comes here with the non-negativity restriction. Here we see that usually x, y, and z are greater than or equal to 0. But here we see that x is greater than or equal to 10, y is greater than or equal to 20, and z is greater than or equal to 30. So this is another type of lower bound. How to solve this? First, we will redefine the variables in the non-negativity constraint, and we will redefine it by considering the variable xyz to be written as x is equal to 10 plus x1, so that x1 will be greater than or equal to 0. Then y equal to 20 plus x2, so that x2 will be greater than or equal to 0. And z is equal to 30 plus x3, that is x3 will be greater than or equal to 0. And this given problem becomes like this. Maximize z is equal to, so instead of x we have x1, instead of y we have x2, instead of z we have x3, and we have extra value in the objective function. Similarly, in the constraints we have x1, x2, x3, and the right hand side has now become as 90 when we substituted the value of x, y, and z in terms of x1, x2, and x3 respectively. And we here see that x1, x2, x3 all are greater than or equal to 0. Now we'll convert this into standard form. What do we mean by converting into standard form? To remove the inequalities and adding slack, surplus, or artificial variables. Now, in this given problem, since x first, second, and third, all three constraints are less than or equal to type, so every constraint, so in every constraint, we have to add slack variable, and after we add slack variable, we get the three constraints converted into equations, and the non-negativity restrictions as x1, x2, x3, and s1, s2, s3 greater than or equal to 0. And we add this s1, s2, s3 in the objective function with 0 as the coefficient, and this is now converted into standard form partially. Why partially? Because we do not have a constant in the standard form. So we need to replace this constant, and it can be done this way. We will reframe the objective function by taking 640 on the left hand side, and we get z minus 640 is equal to 10x1 plus 15x2 plus 8x3 plus 0x1 plus 0x2 plus 0x3. And we replace z minus 640 by another variable, that is z dash, and now we have objective function as z dash is equal to 10x1 plus 15x2 plus 8x3 plus 0x1 plus 0x2 plus 0x3 subjected to the three constraints and the non-negativity restrictions greater than or equal to 0. So this is a regular LP problem now, which we can easily solve. So the first step to solve this problem is to find the initial basic feasible solution. The basic variables here are S1, S2, S3, and we will put x1, x2, x3 as 0. So x1, x2, x3 will become non-basic variables, and the solution would be S1 equal to 90, S2 equal to 150, S3 equal to 70, and Z dash will be equal to 0. So let us formulate a table for solving the LP problem. So this basic table have values of x1, x2, x3 from the three constants, s1, s2, s3 from the three constants. Here in the Cj row, we have the coefficient of x1, x2, x3, s1, s2, s3 from the objective function. And here we have basic variables as s1, s2, s3. And in objective function, their coefficient is 0, 0, 0 respectively. And the solution column, which is taken as the right hand side of the constant. The next step is to find the Zj value, and we get Zj value as all zeros. Then to find Cj minus Zj value, which we get as 10, 15, 8, 0, 0, 0 respectively under x1, x2, x3, s1, s2, s3. Now to find the key column, which is given by the maximum positive value in the Cj row, in the Cj minus Zj row, that is this 15. So x2 will enter the solution as this is the key column. To find key row, we divide the solution column elements by the key column elements, and we get 45, 150, and 70 respectively as the values in the ratio column. The least value out of this is 45. It means that S1 will leave the solution as this row is the key row. And the intersection of key row and key column is the key element. What is the importance of key element? The key element should be made 1, and the other elements in the key column should be made 0. So here we will change the key element to 1 and the other elements of key column as 0. So we have written x2 here as x2 is going to replace s1 and its coefficient is 10 in the objective function. Then in order to make the key element as 0, we will divide the R1 row by 2 and we get entries in the R1 row. Then in order to make this element as 0, we perform row operation on R2 new row. Then we get these values, and similarly we perform row operations on R3 row in order to get these values. So we have found the new values when x2 enters the solution and s1 leaves the solution. We will now start our first iteration. So those values we have put here. You can notice that x2 is the part of basic and its coefficient is 10. Now after finding Zj value, we will find Cj minus Zj value, and we see that only 5 by 2, which is below x1 column, is the positive value under Cj minus Zj. Thus, x1 becomes the key column and x1 will now enter the solution. Now, in order to find out which variable will leave the solution, we will find the ratio, and we find that the lowest ratio is 10 and it belongs to S3. So S3 will now leave the solution, and this element 5 by 2 becomes the key element. So our next step would be to add this x1 instead of S3 and make this key element as 1 and make this half as well as this half which are the other elements of the key column as 0, and it can be done like this. So performing row operation on R3 row will give us 1. Performing row operation on R2 row will give us 0 here, and performing row operation on R1 row will give us 0 here. Now we'll write this again for the second iteration, and we get this table. The next step is now to find the ZJ value and then the CJ minus ZJ value. After finding CJ minus ZJ value, we notice that there is no positive value under Cj minus Zj, and since this is a maximization problem and we need a positive entry under Cj minus Zj for that variable to enter in the solution, so the iteration stops and the final solution is x1 equal to 10, x2 equal to 40 here, and s2 is equal to 90. And after putting this value of x1 and x2 as 10 and 40 respectively in the objective function, we get z dash equal to 700. As the original problem was having distinct variables x, y, and z, so replacing x1, x2, and x3 with x, y, and z, we get x is equal to 20, y equal to 60, and z is equal to 30. And the objective function z is equal to 1340. If you have understood this problem, like and subscribe